Okay, let me pull those up. '26 and 27 from homework 12. Let me find homework 12. All right. Okay, so we've got to figure out how viscosity depends upon mass, right? So we've got to figure that out. So let me go ahead and snip those, put them into our PowerPoint. Let's see. Snip that. And where are we? This one. Okay, so here's 26 and 27. So that's going to be on the viscosity chapter. So let's go up here and look. And so, and I would go to my note card. Let's see, you guys don't have that shown. Let's do this. So let's work our way backwards. And so here's looks like a direct dependence on mass, but also mass is in the velocity. Okay, so we've got a couple of mass dependencies. And so let's break that in. Let's break that into the pieces. Okay, so we've got. Let's just do it right here. So we've got a mass dependency here. Pen, as I always do. I'm going to have to figure out how to mark off the area on my little pad here so I can find my pen. Here it is. All right, so let's look at this right here. So viscosity is proportional to these two items here, and the mass is in both of them. Okay, and so the average velocity, let's see, most probable is 2. The average was 8 over pi. Remember that? Yeah, so it was 8 over pi RT over M. So that's the average velocity. It was most probable was 2 RT over M, and the root mean squared was 3 RT over M, and this is the one in between. Okay, and then we have M here over this business 9 to NA sigma. So what we're trying to figure out is how is viscosity proportional to mass. Okay, so just looking at this, we would say it's proportional to mass over the square root of mass. Does everybody agree with that? I've got a square root of mass here in the denominator, and I've got a mass in the numerator. Okay, so it would be proportional then. How would that cancel? Well, this one is the square root of mass squared, right on top, and so it's proportional to the square root of mass. It's not very well written, but you understand what I'm saying. So let me clean it up a little bit. So viscosity is proportional to the square root of mass. And so we can do eta 1 over eta 2 is equal to the square root of mass 1 over the square root of mass 2. So you see how even though we don't know the cross-sectional area, we don't know, we could figure out all the other constants, pi and r and everything. We don't know what the temperature is, but This is all we need to know. If we're saying at the same temperature, what's the new viscosity? Okay. So let's solve this. I like to do, situation 2 is the new molecule. So situation 1, so it would be eta1. And so then that's going to be M2 on top and M1 on bottom, all to the 1/2. So then we could go to our problem and put those numbers in. So what was the viscosity for H2? 84 centipoise, or what was it? Micropoise. And then it was D2. So we could use 2 for that. So 2 on top. No, 4, right? 4 for D2 and 2 for hydrogen. Those are our masses. All right, so the square root of 2 is 1.41 times 84. So hopefully it's 118 because that's what the answer is. Okay. Yeah, so this is the same kind of problem with the 1s and 2s, but a little bit of added twist, right? You had to dig a little deeper to figure out where the mass is, and to just see that average velocity and go, wait a minute, I think there's a mass buried in there somewhere. So you might have to do a little extra work in that case. I think the next one is similar. Yeah. Okay. Okay, great. Wasn't that fun? The clock is broken too, isn't it? The one in 123 was broken. Now it's fixed. Okay, what's next? I can't tell. Are y'all cautiously optimistic or panicked or what? Don't want to jinx yourself. Okay. Yeah.
I think I got it, maybe 22.
22. Okay. I wish I could mark on PowerPoints, but I mean on PDFs, but I can't. So. So that's on diffusion. So we'll see. Let's go pull those notes up. Thermal conductivity and diffusion. That's that set of notes. Okay. Gonna change. Yeah. Oh, I've got 2 PowerPoint slideshows going. Okay, let's see. Let me escape out of that one. Okay. Okay, so we're looking for the diffusion equation. It doesn't look like it's restricted to one dimension. Okay, so we're looking for the 3-dimensional, and we want time dependence. Okay, so these are all thermal conductivities. We got to find the diffusion spot. All right, here we are in diffusion. Okay, we see velocity there. Here's related to diffusion and based on the particle radius and the temperature, but I don't see any time in there, so we skip that equation. And then here's, again, the concentration gradient. So it looks like this is the kind of thing we need, and it's the square root of time. Okay, so that's the key right there. So we needed to see how far it diffuses based on R or X, but both of these are the square root of time. So we can take that, or I can paste that little question right here. Yeah, it worked. Can you see it? Yeah, okay, great. And so then it's the same kind of question where it's a square root dependence on time. And so we've got this. Oops. Oh my goodness. All right, here we go. Where's my pen? What, I mean, I see the little arrow, but it won't mark anymore. Yeah, there it is. Strange. Okay, so this is R is proportional to time to the 1/2 power. Okay. And so that's 1 centimeter. Okay. And so then we have 1 hour. So we had 1 second, 1 centimeter, 1 second. Okay. And so how many seconds is in an hour? Yeah, 3,600, 60 times 60. If it's 60 times 60, then the square root of that is just 60. Okay, and so that's going to end up being 60 centimeters. So once you find this, I guess this is, again, the take-home lesson in all of these equations, is once you find a proportionality, then doing case 1, case 2 always works. Yeah. And you can not worry about what the diffusion constant is or the coefficient of 6 or 2 or anything like that, because if those things haven't changed, you're just looking at the proportionality. If I change the thing that it's proportional to, and I take into account the proportionality like 1/2 power, or remember the partition function? That was my favorite one. It was the 5/3 or something ridiculous like that, or 3/5 power. Those were crazy, you know. Poiseuille's law with the radius to the 4th power, you know, that one is pretty interesting. Okay. Six? Okay. Yeah, let's snip that. And then 7. 7's the tough one.
Yeah.
That's crazy. Yeah. All right, so let's see. Let me snip both of those. And I always have to, I struggle with 7 because it's always a year between the time I've done it before, and I always come into class cold so that I can work my way through it slowly, you know, and it makes me think every year. That's the best problem ever, because it's such a weird combination of electrochemistry and KSP and equilibrium and everything like that. So that'll be fun. Let's see. Here. just cleaning things up for these problems. Okay. All right, so let's do 6 first. You said 6, yeah. And let's make sure that PowerPoint is ready to go. Yeah, it worked. Okay, I'm shocked. Okay, that's strange. Yeah, okay. I'm just making sure the video records what I do on the screen. So, okay, I think we're ready to go. Okay, so this one we're going to just want to break it into half reactions. The iron one should be really straightforward because so I'll go ahead and set up my arrows. We've got Fe2 plus here, Fe3 plus over here. So there's no oxygens and no hydrogens, so we don't need to add water or acid protons or anything like that. And so we just need to balance the electrons, and you can only subtract. So on the 3 plus side, we've got to add an electron there. So now 3 plus minus 1 is equal to 2, so we're good. So that one's balanced. Okay, so then we, on this one, we have the same number of carbons, the same number of nitrogens, so we have to just jump right to the waters, adding waters to balance the oxygens. So we put 1 water on this side, so the oxygens are balanced, and that is added hydrogen, so we need to add in some H+. So we have 2 of those, so we need to add 2 H+. So now the hydrogens are balanced, and that changed the charge, and so now we need to add our electrons. Minus 1 on the left, plus 1 on the right, actually, because we've got 2 minus 1, so we need an electron here. Okay, so does that work? Or do we need 2? Need 2 electrons, don't we? 2 electrons. Okay. So I'm going to have to multiply this top half reaction by 2. And then I'll bring it down. So this is in basic solution. So we're going to balance it just like normal. And then we're going to make it basic. So that's how I do it. You could, instead of adding waters, if you're going to do it in basic solution, add hydroxides. But this is a more consistent way to do it. It may be longer, I don't know, but I do it this way so I don't ever have to change how I balance an equation. And then at the end, I do kind of like it mentally, I do an acid-base titration. I add as many bases to both sides as I have protons. So let's go ahead and bring everything down. The electrons have canceled. We have 2 electrons on each, so we don't bring those down, but we have 2 Fe3 plus H2O plus Cn minus. Okay, so this is what I missed. Thank you. Very good. Yeah, that's where you mess things up. And so then we're looking at this and we say, okay, I've got acid protons as products, and I want to pull this reaction forward. And so if I put it in base, that's going to pull it forward. So I'm going to add in 2 OHs right here to both sides. Okay, so they come along here. And so these produce 2 waters, right? So acid-base neutralization, and then my hydroxides show up as reactants. But I've got water on both sides, and so I want to cancel those. So I want to cancel this 1 water with 1 of these waters. And then everything else works out. So 2 Fe3 plus 2 OH minus plus Cn minus gives 2Fe2 plus Cn. So that's pretty straightforward. That's how I do basic solution redox reactions, is I just balance them normally and then neutralize the protons and cancel the water. So it's really 2 more steps, but it's a nice conceptually easy step. So, and most of the redox reactions that I come across have protons as reactants, so they take place in acidic solution. But if you have one that takes place, like if you have one like this, where the acid protons at the end of the balancing show up as products, that's going to be pushed forward in basic solution. So that's how you know if a redox reaction is a basic one or an acidic one, is what's in the reactants, what's in the products. Some of them are really mitigated by very strong acids. So there are like bacteria, extremophiles, I guess, that will get in and they will, they produce acid. So they get into mine deposits where there's lots of iron oxide or iron pyrite, iron and sulfur, and they start chewing and living on that iron, sulfur, iron pyrite, and they produce a lot of sulfuric acid. And it's like sulfuric acid draining out all that mine water, and so that's what acid mine water is. It comes from bacteria. So what keeps it from happening naturally? Well, you've got to have oxygen in there. And so it's when we do mining, we open up all of those deposits of iron pyrite to oxygen, and the bacteria love it. So they start growing on that iron pyrite. So a lot of places in Colorado are super contaminated because of this, and it's just natural bacteria and oxygen. Okay, let's do this crazy one. So this is talking about a KSP for AGBR using the electrochemical cell. So this has everything in it. It's got the line notation, all kinds of stuff. So we got to figure out what's going on at the anode and the cathode. So remember, this is in alphabetical order. So the very first thing is the anode. Okay. And the anode takes place at the oxidation. Okay. Or oxidation takes place at the anode. And then we have the reduction reaction. And then we have the cathode. So let's write out our half reactions. So notice this salt bridge right here. This kind of breaks the 2 pieces. So these 3 things here listed, what's our half reaction? That's our first question. This one's easy, right? You've got a half reaction that's silver plus and silver solid. Okay, so let's go ahead and write that out first. Reduction. So we have Ag plus an electron gives Ag solid. It's a reduction, it's gaining electrons. Also, the oxidation number is being reduced. It's going from +1 to 0. So that's the reduction reaction. So that's taking place at the cathode. Now, the real trick is this one over here. So we've got to figure out what the reactants are. And so focus on the bromine. So we have bromine attached to silver, and then we have bromine ion, and it's going to be an oxidation. Okay, so we got to write that in a way as it is an oxidation. So let's just, like over here on the side, do some scratch paper work. Okay, so let's balance this. We have AgBr going to Br minus. And let's balance the silver. So this is AgBr solid. This is Br minus aqueous. And we need to balance the silver. And notice it's in contact with that silver electrode. So it's probably going to be silver solid. Okay. And so we're looking at this reaction and we're trying to figure out, well, how do I write this as how do I write this as an oxidation? So we don't have any oxygens, we don't have any hydrogens, so we're left with the electrons. So we got to put an electron on the left, right? Left, not right. Left, correct? Okay, so if I were to write this over here on the right as is, it would be backwards. We need an oxidation. And so I've got to flip this whole thing because we need a reduction and we need an oxidation reaction. So I've got to reverse this thing and write it with the AgBr solid here plus 1 electron, and then we have Br aqueous Ag solid. Did I get everything? Yeah, I got everything. All right, so that's our electrochemical cell, the 2 half reactions. What stops you? Like up to this point, were you able to get this far, I guess? Mm-hmm. Say that again.
They're like finding the numbers to like the half reaction.
Yeah, so if you go digging around in the reaction table, you might find these 2 reactions and you compare them up. But I was just trying to go from the line notation in case we didn't have that table. Now we're going to need the table for the numbers for sure. Yeah. But anyway, did that make sense though? We need a reduction and we need an oxidation. So we have to have the electrons on opposite sides of each other. And so then that's why I had to flip that reaction. So then we go ahead and cancel everything down. And this is the cool thing. So the electrons cancel, that's fine. But look, the silver solids cancel. And that's pretty cool because then we're left with Ag plus aqueous plus Br minus aqueous, giving AgBr. So, which is our KSP type, solubility problem backwards. Okay, so if we can get the equilibrium constant for this, if we reverse this reaction, it's 1 over that equilibrium constant. So this is going to be a spontaneous reaction because these 2 things precipitate out. So it's going to be an equilibrium constant that's large because it lies to the product side. But if we flip that, the equilibrium constant is going to be really small, and we'll have the KSP for silver bromide. And so all we have to do is measure the voltage of this cell, and we get the KSP. So that's pretty cool. So let's go ahead and do the voltages. So let me just make some space here for it. So what is the voltage for this first reaction from the table? Do I need to pull up the table that you'll have on the exam? Okay. Let's see if I can. It's probably, I think it's on there. I'm not sure. Let's see. It's 0.8 for the silver ion. Okay, 0.8. So let's go ahead and do that. 0.8. This down. All right. Plus 0.8. Okay. Yeah, for that's a reduction reaction. So you don't have to change the sign. For the next one, we'll have to change the sign. I'll try to pull up that table. Exams. I've got so many files on my computer. It's crazy. Thermo and redox tables. There we go. Okay, where are you? Yeah, it's not on the exam one because I don't ask this question on the exam. So I thought it might be. It's not in the class one either. Let me pull up the textbook then. I've got a PDF of the textbooks. Thank you for being patient. Here we go. Reduction, half reactions. They're not sorted, of course. I mean, they're sorted in terms of decreasing. Okay, here they are. They're sorted in alphabetical order. Found it. So let me grab a snip of that just so you see what I'm looking at. Okay. Let's see, which one is that? That's on the viscosity. Did it appear?
Yes.
Okay, good. All right, here we are. So let's go back to the slideshow. All right, so we're looking at this table and we can see that it's 0.08, but it's written in reverse because it's an oxidation reaction. So it's minus, let's see, my pen, minus 0.0713. You don't need all those extra decimal places, but volts. And so that'd be 73 volts. All right, so that's the E cell. Now, how do I get to equilibrium constant? Because we want the equilibrium constant. This is a great problem. We got to figure out what the oxidation and reduction reactions are. We got to use line notation. We got to find the cell potential, but we still aren't to the equilibrium constant. The what? Think about where let's work backwards. We want to get the equilibrium constant. What value can I use to calculate the equilibrium constant? Well, think about this. We've got the reaction written out here. And so, okay, let's do that. So we could say K is equal to, the way it's written, 1 over the concentration of silver ions and 1 over the concentration of bromine ions. So that's K, right? Does that make sense? That says that we've got the reaction, that's K. 1 over that would be KSP. That's where we're actually getting to in terms of the problem, right? So 1 over that, so 1 over K would equal KSP. So that's the end of the problem when we get there. How is E cell related to K? That's the trick. Is E cell related to any other thermodynamic values that we could use to get to K? Delta G, that's the one. So we've got to go through delta G to get to K. And I've got E cell, now I can calculate delta G. Okay, so let's go ahead and write this out. Delta G, I'm just going to write it up here in the corner. So delta G is equal to minus RT ln K. So that's the delta G relationship to K. And delta G is also equal to the E cell equation. What is that one? Minus NFE. So there's my connection to K. So from this positive 0.373, I could calculate my delta G. So delta G is equal to minus, what is N in this case? So I'm looking at this reaction. Since I balanced this reaction, I know what N is. It's the number of electrons exchanged, so that's 1. Okay. One mole of electrons. Faraday's constant is 96,485 joules per mole per volt. Okay. And then I've got volts here, plus 0.73 volts. So my volts cancel, my moles cancel, and I got joules for my Gibbs free energy. And it's negative because I have a negative sign out front. So I've got a nice spontaneous reaction. So I could have asked you that question too. What's the Gibbs energy for this reaction? So when you get your number for delta G, go ahead and give that to me. Negative 7,424. 704. Go ahead and read it up to 7043. Is it the decimal place right here? Oh. 70434. Okay, 34. Okay, that just to the ones place is fine. We started with two significant figures. All right, so that's that divided by 8.314. So that's joules. Let's go ahead and use our units so we don't screw up. That's in joules, correct? Yeah. Now, there's always this discomfort here. That's joules because we calculated it, but it's for 1 mole of all those substances. So there is an implied per mole here, so that it'll cancel the per mole in the arc and the gas constant. So don't be. That always gives me heartburn too. It's like I have joules and now I need to cancel a mole, right? But it is for 1 mole of the Ag, 1 mole of the bromine, 1 mole of the AgBr. So there's an implied per mole there. So divided by 8.314 joules per mole Kelvin, and then that denominator has a 298 in it too, temperature. So it's divided by both those numbers, multiplied by each other. Okay, so that's a long calculation, but notice the negative signs cancel. That's the really important piece. What'd you get? 2.2 times 10 to the 12th. Should be big because it is a insoluble substance, so it's going to lie to the right, so that's good. And so then we take 1 over that. See this equation here, 1 over that number is the KSP. So we got the right answer. So we did it right. So it's close to 2, so 1/2 would be 0.5, and so that's where we get the 10 to the negative 13. We had a 10 to the 12, so it was like 0.5 times 10 to the negative 12, and so that's 10 to the negative 13. So that's fantastic. What a long problem, but that's why it's on the homework. Am I going to give you this whole thing on the test? No, because you wouldn't finish the test. But isn't that a great problem? That is just beautiful. And it's everything in it. Gibbs energy, equilibrium constant, KSP, for goodness sakes. That's Gen Chem 2. And that's also a really neat way, if you had this electrode set up with silver and bromine and everything, that you could measure the KSP electrically, right? Because I always wonder, how do they measure these really small, like 10 to the minus 13 KSPs? You know, are you really going to measure the concentration of bromine ion in that solution down to 10 to the minus 13? That's a really small concentration. So how would you measure that? Well, electrochemistry is a way to measure some of these things. So it's kind of a gee whiz type deal. It's like, okay, that's how you would measure some of these really small reaction equilibrium constants. Cool. Which one?
15. I just wasn't sure.
Okay, let me look at that. I can't find my mouse. On number 12, 15?
Yeah.
Okay. Okay, so this is the thing. We get the biggest difference between, think about the differences. You want the largest difference in mass, but you want both of them to be as small as possible.
Okay.
So there's two things at play. So yeah, you might have a big difference between two really heavy masses, but it'd be hard to separate them because percentage-wise, it's not a big difference. So you want the largest percent difference. So going from like hydrogen to oxygen would be a huge difference versus, well, is there another, like fluorine to chlorine? Fluorine is, so that'd be 36 and 70. 36 and 70 might be a bigger difference, but it's not a bigger percentage difference. Yeah. So okay. Well, we're kind of out of time. Is there anything else that was just burning in your head? Okay. Are you comfortable with the ionic strength calculation? And look at that, because I just wrote the test, so I know this is on there. So look at the difference between the thermodynamic and the concentration rate constants. So let me just show you that real quick on this. This page is kind of full, so if I go to the next one, no, I don't have enough to go to the next one. Okay, this will be worth it. So just stay 2 minutes later. Okay. Yeah, okay. So let's just say for this generic reaction, okay. So if we have, gosh, let's try to do this quickly. A plus 2B gives C, 3C plus 4D. Crazy reaction. Okay, so K is obviously equal to it's the activity coefficient for C cubed, activity coefficient for D to the 4th power over the activity coefficient for A. So it looks the same as the concentrations, but the concentrations are also there. C cubed D to the 4th I made this way too complicated, but it gets the point across really well. Okay, so this piece right here is K prime. The concentration, concentration. Does that make sense? That's what you learned. And then this whole thing, because we've corrected that, is the thermodynamic thermal equilibrium constant. I just want to reinforce that vocabulary, right? Because if you don't know what those two words mean, the differences between them, you can't do that problem. Okay. And so, like, if you're given all of these, like if you know this and you know all of this, okay, then you can calculate that, right? And so that's the way the problem is. If you're given the activity coefficients and you know the thermodynamic equilibrium constant, what is the concentration equilibrium constant? Well, if you don't know the difference between those two, you can't do that problem. But now you do. So I just gave you a huge hint. There's an extra, 3 or 4 points for you. All right, good.